Okay, good afternoon, everyone. This is our lecture 5. And before we start our lecture, do we have any questions for our last lecture or previous lectures before we continue about multiple testing? Okay, one thing I want to clarify about the homework, this is also applicable to your research, I think, is about how you can generate like R markdown file using RStudio, or you can also do a similar thing for Python using the Python notebook. So anyway, you can generate a markdown file, which includes your code chunks as well as your results. So a question I received is regarding how do we run the code that takes a long time to run, right? You cannot afford to rerun everything once you compile the file. My suggestion is that for those time-consuming code chunks, you save your results to some intermediate files. And then when you knit your document, you only load the file to run the figure generation. So that can save you a lot of time. And this is a very useful technique for your research work. Like for your research papers, a lot of journals nowadays require authors to make their code or results reproducible. So you need to submit your code along with your manuscript. But in that case, if a lot of code need to be run on a server or take a long time to run, you cannot expect your readers to reproduce everything from scratch. So in that case, you need to save a lot of your intermediate results as files and provide them to your readers. So this is something we all do in our research. Another useful thing to do that is that can also save you a lot of troubles when you're running those code on server. Sometimes we may run into some unexpected issue that the code just randomly stopped without a reason, probably due to some RAM issue or internet connection issue. So for those cases, it's always safe to save intermediate files. So when you need to restart the code running, you don't need to start from the beginning. Okay, so that's just a suggestion for the homework. Now let's continue our discussion about multiple testing. So the context is that we need to do multiple tests simultaneously or in parallel. So for example, in the detection of differentially expressed genes, DE genes, we need to test P genes in total. And each gene has its own hypothesis to be tested, right? The null hypothesis is always that the gene is not DE. And we want to use the test. And if we reject the ith null hypothesis, we would call the ith gene as DE. So here, there's a definition of true positives, true negatives, false positives, and false negatives. So we will start from there today. Let's look at this so-called a decision matrix, or some people may call it a confusion matrix. It's basically the same thing. So the matrix is a 2x2 matrix or table. And we have our decisions in the rows. Okay, so our rows are decision. And in this hypothesis testing, we have a binary decision for each test. That is, we reject or we do not reject. That null hypothesis. And for the columns, it's about the unobserved truth. And the truth is that the null hypothesis is false or the null hypothesis is true. So if we say that, so to be consistent with our notations in the notes, if we say that we have a total of M hypotheses, so this is the total number of H zeros. So suppose that we have a total number of 8M hypotheses, then this 2x2 table will summarize our decision results in relation to the truth. So of course, the truth is unknown to us, but let's try to assume it's known for now. Yeah, there's a hand. What's the question?
Yeah, I think I cannot like see the table fully. Like,
oh, sorry. Okay. Thank you. Thanks for letting me know. Yeah, so this is there. We have a total of m hypotheses, and we will divide them into, so let's call them the total here, and also we have a total here. If we call the total number of rejections as R, then clearly we have no rejection as m minus R. And if we consider the number of true null hypotheses to be m0, which is also unknown, then the number of false nulls is m minus m0. So we have these totals here. And then we will give a notation for each entry. So we call this S, V, T, and U. This will help us with our later discussion. So in our notation here, we would call this, okay, so if the null hypothesis is false, which means that the gene is truly DE, and we reject it, right? Then that's good. This is what we call true positive. Positive means we reject it. And if it's a true correct rejection, we call it true positive. So similarly, when the null hypothesis is true, which means that the truth is that D is not DE, and we do not reject it, which means we have a negative, and it's a correct negative, we call this true negative. And then here, when the truth is negative, but we reject it, right? Our rejection means that we make a positive call, but it's a wrong positive call. So we call this false positive, and the last one is false negative. So I know that in some papers, people may define these four terms in different ways, but this is what we define. Okay, do we still have a question, Jingyuan? Your hand is still up. Oh, okay. All right, so yeah, so let's just keep in mind that the true positives are the identified DE genes that are correct. True negatives that are the identified non-DE gene, non-identified non-DE genes that are correct. And false positives are the DE genes we call, but they are wrong. And false negative are the ones we didn't call, but they are DE. So these are the four terms we'll play with. And related to these four things, there are several metrics in bioinformatics you will see in research papers. So I will just briefly discuss them in a very quick way so that we can clarify their terminology. So let's still look at this table. So the first term you will see in a lot of cases is what we call precision. So precision is actually the percentage of true positives among positives. So in other words, it's TP divided by TP plus FP. Or you can see TP plus FP is R. It's the total number of rejections, or the DE genes you call. Among it, how many of them are true positives? This is precision. Another metric that's widely used is called recall. So recall means that among the true genes that are DE, how many do we find as DE? So the true gene that are DE is here. So true positive plus false negative. This is the truth that are DE, and among which the percentage we call as TP is the recall. So in other words, you see TP plus Fn equals n minus Nn. So these two things are commonly used. Another thing we often use is the called true negative rate, short as TNR. So true negative rate is that among the negatives that are the truth, how many do we identify as negative? So the negative that are true, that's here, the second column. So it's actually FP plus TN. Among which, how many do we call as negative? That's TN. So in other words, it's TN divided by M0. That's true negative rate. So you see a key difference between precision versus recall and TNR. So if we consider it precision versus recall and TNR. The reason I put these two on one side, precision on the other side, is because in the denominator, precision, the denominator precision is related or it's determined by our decisions. It's the number of rejections. So this is based on our decision. While over here, their denominators are only based on the truth. So that is a very important difference, especially in our statistical analysis. The reason is that we understand the rejection decision is data dependent. And as we know that data is random, then the rejection decision is random. So just a reminder, the data is random because we consider repeated sampling in the frequentist paradigm. So under repeated sampling, our data is one of the possible realizations of our sampling. So the data is random, so the rejection and the decision is random. While in the frequentist paradigm, we consider the truth to be fixed. So the natural consequence is that if we do statistical analysis on the precision, it's a lot more difficult because both the numerator and the denominator are random. So two random quantities. But if we consider recall and TNR, only the numerator is random, but the denominator is fixed. Okay, so a related concept here is what we are going to define today. So let's just hold that for 1 minute before we summarize what we said last time. So how do we evaluate the degree of false positives in our multiple testing result? Okay, so let's put it here. So we have three, let's put it here, 3 criteria for false positives, which means that we do a rejection and it's false in multiple testing. We have already covered 2 last time. The first one is what we called per comparison error rate. So we will write this in short as PCER. Okay, what does it mean? So it's actually the average type 1 error of our tests. Or in other words, we can say that it is the probability that one null hypothesis is falsely rejected. And to be more precise, we should write it as the probability that any null hypothesis is rejected. That's our decision, given that the null hypothesis, the ith null hypothesis is true. So if we want to control this under alpha to control this PCER under alpha, we just need to set the significance level for each test to alpha. Set the significance level of every test to alpha, and then we're done. So that's the case where we just say if we set alpha to 0.05, let me put this simpler. If alpha equals 5%, 0.05, we reject H0i, the ith null hypothesis, if its p-value, pi, is less or equal than 5%. We're done. So this is the way we will do if we do not learn this multiple testing at all. However, as we said, this per comparison error rate is not so meaningful because the number of false positives would linearly increase as the number of tests increase. So that's the problem. The issue is that the number of false positives, so basically this is the false positive, or I should just say this. Maybe I should just say false positive may be too large. And that's not good. So for example, if we have 1,000 tests, that's the example we gave last time. If we have 1,000 tests here, and we have set a significance level or per comparison error rate to 5%, we would expect to have 50 false positives. So if all of them, all the 1,000 are true, the null hypotheses are true, we will still expect 50 rejections, and they are all false positives. So to a biologist, in this case, this is clearly undesirable. So to address this issue, the second criteria is what we said last time, is the family-wise error rate. So the family-wise error rate is to control the false positive number as a whole. So no matter how many tests I do not want to have any single one false positive. So using our notation here, this error rate is defined as the probability that V is greater or equal than 1. So whenever V is not 0, we consider that we make a family-wise error. So last time we showed that to control this family-wise error rate, a very stringent criteria under alpha, we can use Bonferroni correction, which is the most conservative way to ensure this. So we said the Bonferroni correction is very simple to implement. It's basically to set the significance level of each test to alpha divided by m. So that is, you divided, say, 5% by the total number of tests. So this is very stringent, and you can be very safe in terms of not having too many false positives. But the issue with this is that it's often too stringent. That is, this number is too small. So you do not make any rejection. So let me just give you an example. Still, when alpha is 5%, you reject this H0i if Pi is less or equal than 0.05 divided by m. So you can do a calculation to see when m is 1,000, how small this number is. And it's possible that none of your p-values are smaller than this threshold. So the issue is that you are being too conservative and you cannot make any discoveries from your data. That's also not desirable for biologists. As a result, a third criteria was proposed in the middle of the per comparison error rate and the family-wise error rate. So the third one, we call it false discovery rate. And that will be the focus of today. Okay, so what do we do here? Using the notations, we can define the false discovery rate FDR as follows. It is defined as the expectation of V over R. In other words, among the rejections, the proportion of false rejections, and we take expectation. This expectation is respect to random sampling. As we said, the decision is random, so R is random, V is random. And if you take a closer look from what I wrote before, This can be regarded as 1 minus the expectation of precision. Because, let me scroll up, you see in the definition of precision, we are doing TP divided by R or S divided by R. So this is just the realization on your data, but we are just calculating this as a number. It's not an expectation. We didn't consider other possible samples. But in false discovery rate, we are not just concerning this particular value, we are concerning its expectation. We want to control this expectation under alpha, similar to this family-wise error rate. So you see, when we write the probability, we are considering possible resampling, possible sampling, because this V in particular, it's a random variable here. If just based on our data set, we have a realization, whatever number. But when we consider other possible data sets, we can talk about probability. We want it to be basically what the probability means that we apply the same decision procedure to many data sets. And out of the many data sets, we expect that the probability that we make one false positive is going to be under 5%. That's the family-wise error rate. And in the FDR, what we want is that applying our procedure to many data sets. For each data set, we can have a false positive ratio. So there's a name for this. So this V versus R can be called false positive proportion. So that's the proportion on one data set. And once you take the expectation across data sets, you are talking about something on average, and that's the FDR. Okay, but you know that whenever we have a division, it's always to keep in mind that the denominator cannot be 0. But if you look at the denominator here, it's R, and R could be 0. Whenever we do not make any rejection, our R is 0. Then we have a dividing 0 issue. How do we address that? We just make a special case by setting it to 0. So when this means otherwise, when R is 0, we just set FDR to 0. This is the definition of FDR. So then the goal is to control this FDR under some pre-specified alpha, 5% say, and then find the corresponding threshold on the p-values to achieve FDR control. So one thing to note about the definition of FDR, which is a very important property about expectation, just to say that for your information, is that the expectation of the ratio is not equal to the ratio of expectation. Okay? You can see why this is. The reason is that you know x1 over y1 plus x2 over y2 is not equal to x1 plus x2 over y1 plus y2. This is the fundamental reason for this. So, you know, when we take expectation, it's essentially we're taking some sort of average, and the average is always based on summation. So that's why whenever we don't have this, we do not have this. Okay, so the thing I want to introduce today is a very famous algorithm or procedure for achieving the FDR control with p-values. So I would say way to control FDR under alpha %, we can use the procedure called Benjamini-Hochberg procedure. Let's call that as BH procedure in short. So it's a way to find a proper threshold on p-values to achieve the FDR control. So let me first introduce the procedure, and then I'll explain why. So the procedure requires a first step of sorting p-values from smallest to largest. So after we sort them, we give the sorted p-values a parenthesis in the subindex to mean that this is after the sorting, the smallest p-value, so that we can differentiate this one, this p parenthesis one, with the original p1, because that is the index before sorting. So let's do this up to pm. And then we will denote their corresponding null hypothesis to be tested. Corresponding null hypothesis as H0. Probably I'll just write this. H01, H02, H0M. That's the corresponding null hypothesis. Okay. And then step 2 is to find the threshold. So if I use a graph, it becomes very illustrative. So what we do is that we actually let this to be the rank I, and this is the sorted p-value pi. So we will actually set the alpha to be here. That's the target alpha for FDR. And of course, this is between 0 and 1. We know all the p-values are between 0 and 1. So what we do is that we find the line, which actually is a straight line. This is alpha here. It connects 0 to this alpha. So we know that in this alpha, the slope is alpha divided by m. Okay, so the slope is alpha divided by m. For example, when I equals 1, y equals 1, we know that this value is just alpha divided by m, and the other value here is just alpha divided by m times 2, and so on. So we get a value here for each I. And then what we do is that we compare the corresponding p-values here. So suppose that I have a p-value here, 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 and here. So in the BH procedure, what we call is that we will find the largest I such that the p-value is below the line. So for example, here we will pick this one. Because you see, after this number, the next one will have its p-value above the line. So in other words, we start from here, I equals 1, we trace the p-value, compare each p-value to this line. If it's below it, we keep going, unless we have a violation. Once we have a violation, we go back to the previous I, and we call that this rejection. So in other words, we're going to reject everything here.
Dr. Lee,
so every p-value on the left of this line will be rejected. And what does this mean mathematically? So we can say that we pick K as the largest, we can say as the maximum of the I's such that the I's sorted p-value is less or equal than I times alpha over m. This is the slope. And this represents the value in the line. So as long as we have this pi less or equal than that, we take the maximum of I, and then we are fine. Okay, so this is how we pick the K. And then this is the corresponding, the largest p-value that will be rejected. So you see the p-values for every p-value. So if every p-value is, so for the p-value is less or equal than this pk parenthesis, that means the chosen K, and that's the largest one after sorting, right? So as long as any p-value is less or equal than that, we reject its corresponding null hypothesis. So in this example, we are going to reject these 4 null hypotheses based on this criteria.
Dr. Lee, can I ask a question?
Yeah.
Is it possible for it to go above that line and then back underneath, in which case we would keep going, or does that not occur?
So that's a very good question. So basically, the p-value, you know, they cannot decrease for sure.
Correct.
Because
Yeah.
that's the story. But it's possible that the increase in degree, like probably this one increase a lot, so it goes above, right? And then you actually have something that goes increases slower, right? Or it stays the same, so it becomes lower than the line again. So based on my thought, I think that's a very interesting question. I think what we do is to just, as I said, so probably a better way to write this part is to say that we need to have everything we need to have this hold for all the j that's less or equal than I. Probably that's a better way to write it. Yeah, so maybe I'll change it a little bit. Yeah, so pj less or equal than j times alpha over m for all j less or equal than I. So that can avoid the issue you just mentioned. Yeah.
Thank you.
Okay. Yeah. Then, so let's first look at this intuitively to say why this is less conservative than the than the Bonferroni correction. Okay, we can compare the three things for now before we explain why the BH procedure works intuitively. So let's compare the three procedure. So I'll call this the rejection threshold on the p-values. Okay, and we consider three criterion. So we have the PCER, and we have the family-wise error rate, and we have the FDR. And our goal is to find the p-value threshold so that each criterion is under alpha, less or equal than alpha. So if we want to control PCER under alpha, our goal is to just set pi less or equal than alpha, and we're good. If we're going to control family-wise error rate, we're going to set pi less or equal than alpha divided by m. And finally, for the FDR control, we are going to compare pi, the ith p-value, probably put it this way, less or equal than its rank times alpha divided by m. So in other words, you see, for the first two criteria, the threshold has nothing to do with the rank with the rank of the p-value among all the p-values. So we're just looking at each p-value individually, and we set a common threshold. So clearly, this is very large, this is very small, and this one, why can we make more rejections? The reason is that the threshold increases as the rank goes up. So it's possible that we can make rejections. So for example, like for the first one, you see, for I equals 1, the threshold is just alpha over m. But for I, let's say, equals 10, then the threshold is 10 times alpha over m. So it's getting bigger and bigger and bigger. So it's possible that we can make more rejections, not just comparing the threshold of the smallest one, right? But for the FWER, family-wise error rate, we're comparing every p-value to the most stringent threshold. So it's very unlikely that we'll have a lot of rejections. And so in other words, you see that the essence is not about our tests. Our tests are still the same M tests, and our p-values are still the same M p-values. What's only changed is the criterion for setting for thresholding p-values. So we are changing our criteria to make more discoveries. That's the essence behind multiple testing. So you see that why this FDR is more reasonable than the PCER, right? This will give us, if we set the number of rejections, or we can call this R. So this PCER will have the largest or most rejections, and this FWER will give us the fewest rejections, and this is in the middle. So you can see why this is more reasonable than this one. It's because no matter how many tests we do, we are controlling the ratio that is of our interest. That is among the, for example, in our DEG analysis, among the DE genes we identify, what percentage are false positives? As long as we can make this ratio quite small, V over R quite small, we should be pretty confident with our results for downstream for further analysis. So that's just the fundamental reason why FDR is so popular, because it's more reasonable than just the PCER, which does not do any multiple testing correction. And it will give us discoveries more than what we can using FWER. So it's like a trade-off between what we can achieve and what is not desirable. So I hope that makes sense to you. So finally, now we know the FDR concept and the BH procedure. It's a very simple procedure, like everyone can do the code yourself. Then the final important question is why can the BH procedure control the FDR? So to formally answer this question, we need to have some strong background in probability. So for example, I would say the most current or what people use widely, the proof will use the concept called Martingales. So that is an advanced probability concept. So without using that, we will just be able to give you some intuition behind how it works. Okay, so let's take a look at the very intuitive understanding why BH works. Okay, so to do that, we need to first analyze this ratio, this expectation of V over R. So we are going to do a conditional argument to make it simpler for us. So we just condition on R equals K, because you see K is what we picked, which means that we will reject the first K sorted p-values. So conditioning on this is a common technique we use to deal with expectation. Then you can see that the conditional expectation of V divided by R given R equals K is much easier to analyze, because now the denominator is no longer random but fixed, and we're only considering the randomness in the numerator. So then I can get the K out, and then I'm left with expectation of V. Okay, and what is the expectation of V, which is here? The expectation of V, the false positives. So this will depend on our significance level and also our number of tests, right, M. So you can see that basically, given the BH procedure, as I wrote here, essentially, we are setting the significance level to the sorted kth p-value, because anything below it will be called as rejection. So in other words, the expectation of V can be less or equal than the total number of tests times the significance level we actually place on p-value. That is pk. Because the k is treated as fixed, so the k can be considered as fixed. And then I can have this divided by k. And finally, this will help me, that is, the pk itself must satisfy this criterion by comparing its value to the line. It must be less or equal than the line. So we would have m divided by k. Pk itself must be less or equal than k times alpha divided by m. right? That's how we pick the K. And then by cancellation, we get alpha. So this is a very short intuition to give you why this will work by conditioning argument. But as I said, to make this more rigorous, we need to use more advanced probability to achieve that. So this is the FDR, this is a BH procedure, and the more widely used criteria is what we call Storey's Q value. So I'll just briefly introduce this for your information. So roughly speaking, what's the difference between these two things is that based on the BH procedure, what you do is that you need to first set, probably should just figure, you need to first set your target FDR alpha. Then given alpha, you find a threshold on your p-value. And to threshold your p-value and make rejections. But what if you don't want to set alpha beforehand? You want to provide people with something so they can threshold the FDR as they wish. So the Q value serves this purpose. So you can consider it's a way to convert your original P values to some Q values so that if you want to control the FDR under alpha, you directly threshold the Q values. That's how it would work. And so intuitively, you would basically do this P1 to Pm, the sorted P values, you convert them to Q1 to Qm. And please note that the rank stays the same. This conversion does not change the rank. The smallest p-value is corresponding to the smallest q-value, and the largest p-value corresponds to the largest q-value. So the rank stays the same. And what does this conversion do? It's kind of relying on the BH procedure, but there are some slight differences. So for example, in the BH procedure originally, sometimes we may find that if we set the alpha, we vary the alpha, by increasing the alpha, the corresponding p-value threshold is not necessarily increasing, it's not necessarily monotone. So that therefore, in the Q-value conversion, they try to force this to be monotone. So you keep the rank. That's the key change in there. And also, in terms of the definition, there's a slight change, but I would not emphasize that too much, is that the Storey's Q-value is trying to control something called positive FDR, which is slightly different from FDR in that it's a conditional expectation for R to be positive. So in other words, if you compare this definition with this definition, this one and this one, so you will see that difference. Yeah, this is the original definition of FDR, and this is the definition of positive FDR. So there's a slight difference between the two. So you don't need to worry about the R being 0 here. And then basically the Q value is designed to, if you threshold this, let's say if you cut the Q value by alpha here, based on your choice of alpha, you can control the positive FDR to alpha. So this is what people use a lot in bioinformatics, Storey's Q value. But I would say the fundamental, the basis or the foundation is still the BH algorithm. So hopefully you will find this something useful. And also for your information, my own research group recently developed a method called Clipper, and I want to advocate it to our bioinformatics community. So the key novelty there is that we try to get rid of the use of p-values or multiple testing for controlling the FDR in biological data analysis. So for example, let's say we're still doing the DE gene identification. But one thing that's needed for p-value calculation is that you need to have a valid null distribution for your test statistic. Otherwise, for the p-values corresponding to the null hypothesis that are true, you will not expect to have a uniform distribution from 0 to 1. And this is actually in your homework. So in your homework problem, I asked you to plot the p-values for the true null hypothesis to check whether they are indeed uniform between uniform 0 and 1. This is something that's very important. I'm going to emphasize it. So basically, Fdr control relies on valid p-values. And some people call this valid p-values as well-calibrated p-values. Instead of versus, so instead of, if people call this invalid p-values or ill-post p-values, so you will see those terms. So these p-values are bad. If you use those, then the Fdr control will fail. So what we mean by valid p-value is that, so for the pi's, if the H0i is true, the pi should be drawn uniformly from 0 to 1. That's the requirement of a p-value. And this can also make you realize that the p-value is actually a random variable. It's not a fixed constant, it's a random variable. Why is that? If you think about it, in the t-test case, right, what we define is that pi is defined as the probability that our test statistic is greater or equal than, so I'm going to maybe do a two-sided t-test. The t-test statistic is it's greater or equal than our observed ith t statistic value under the null hypothesis. Or probably I should do this. Okay, so this is saying that under the ith null hypothesis is true, if our t statistic considering possible sampling under the null hypothesis, if the absolute value exceeds the absolute value of our observed test statistic in our data, we call this probability the pi. So in other words, there is a 1-to-1 relationship between the pi and the lowercase ti. Let me put it this way. This is what we observe from our data, and we convert it into a p-value. So as long as we are aware that this ti itself is random, right? Let's say we change our data, this observed test statistic value will change. Then correspondingly, this p-value would also change. But if this distribution is right, so if this p is the correct, based on the correct distribution of the test statistic ti given the null hypothesis, then a natural result is that pi would be uniform 0 to 1. This is actually a very important, phenomenon in our probability or random variable distribution. So the essence is this. So the underlying fact for this, let me explain this, is that, so let's say if x follows a distribution f, and this f is its cumulative distribution function, or we call it CDF. This is in the probability class. So if we say that random variable follows this, then we can say that if we apply the f to this x to do the transformation, this transformation will follow uniform 0 to 1. That's just a very important fact about our probability. Why is that? If you think about it, this is just based on a transformation, and this transformation basically flattens out the distribution of the random variable. And to show that exactly, we can take a look at this fx. Probably I need to just add one more thing to say that if I change this to fx, what it means is that f lowercase x is defined as the probability that the big X is less or equal than lowercase x. That's the CDF. But what I'm saying here is that I just changed the argument to be the random variable itself. So it becomes a random thing. This is a function. There has no randomness here. But once I change the argument to be a random variable, this becomes a random variable. And this transform random variable is uniform 0 to 1. And why is that? We can easily show that by one line of proof. Just that the probability, let's say, fx less or than t, okay? So we know this fx is between 0 and 1 because it's a probability. And suppose that the CDF itself is invertible, okay? So let's say that this function has an inverse in the simple case. Of course, we can prove it for the more complicated general case, but let's just do the simple case. When it's invertible, this probability can be written as x less or equal than f inverse t, because CDF is always monotone. And now, this is just based on this can be related to the definition of the CDF here. You see, x less or equal than some constant, the probability of that is the definition of the CDF. So this is equal to f evaluated at f inverse t. And that gave me t. They get canceled. So this is exactly the definition of a uniform distribution, because you see, if we have a uniform distribution between 0 and 1, and if we plot the density is just flat, right? This is density is flat. And we know that for t here, the CDF is the area to the left of it, and so the area is also t. So this is exactly the definition of a uniform distribution. And what I want to say is that this fact is essentially why the p-values are uniform 0 to 1. Valid p-values should be uniform 0 to 1. But if the null distribution is mistakenly specified, for example, if the test statistic should follow chi-square distribution, but you misspecified it to be a t distribution for a test statistic, then of course, based on the wrong null distribution, the p-values will be wrong. Then therefore, no matter what procedure you apply, the BH procedure will not guarantee the FDR to be controlled. And this is a very important issue to pay attention to in bioinformatics, because I can tell you that if you read our manuscript, many popular bioinformatics tools cannot really effectively control the FDR to the target. And the reason for that is because the p-values are not well calibrated. Okay, so just to summarize, the three essential components for a valid statistical test, or I would say 3 components for statistical tests, for a statistical test. Let me just say one test. The first one is that you need to specify the test statistic. And this is based on the null hypothesis. The null hypothesis and the alternative hypothesis. These two are based on your scientific question, the question you want to ask, such as differentially expressed genes. And the second and the most tricky step is to derive the distribution. The distribution of the test statistic under the null hypothesis, under H0. And we said that we have multiple ways of doing this. So parametrically, you can derive it using mathematics. So for example, in classic textbooks, we have the t-test. That is a parametric test. Or we have the f-test, right? Those are all parametric tests our pioneers have derived for us. But if you do not know how to derive the distribution for a new test statistic, a simple thing we taught you is to do permutation, to create and other non-parametrics like well-Coxon. So In that, oh, sorry, I should delete that here because that's related to test statistics. Sorry for the confusion. So permutation is another way for you to derive the null distribution. And that is by randomly shuffle your data, and then you create some data that do come from the null. And using those permuted data, you compute the test statistic, and their values should come from the null distribution. As long as you can do the permutation for many times, you will have many values under the null, and that can help you form, estimate, or construct a null distribution. That's a common procedure, but we have to be aware that this is computationally intensive, and this requires your sample size or number of data points to be relatively large. Otherwise, there's nothing to permute. So the third thing is what we said today, is to set p-value threshold. Right, given these two things, you will be able to compute the p-value. And the last step is to set a p-value threshold. And for this, if you are doing a single test, it's easy. The threshold is just your significance level, 5% usually. But if you're doing multiple testing, you need to be aware that the total number of false positives may be too big if you do not account for multiple tests together. So in that case, we talk about the very stringent family-wise error rate, which can control the overall that you do not want to have one false positive. That's very stringent. Or you can consider the less stringent false discovery rate as a threshold. So for that, the commonly used procedure is the BH procedure and its derivative, the Q value idea. So using either case, ultimately, you will be able to set a threshold on your p-values to make decisions. Okay, so I have said enough about the importance of having valid p-values. So you could check out our paper for doing this FDR control without using p-values. So what we do is that we totally save the second step. We don't need to derive the null distribution at all. And this is very good for biological data when you do not have too many replicates. Imagine that if we are detecting DE genes from two conditions and each condition has only 3 replicates, like in the case we talked about, 3 versus 3. In that case, it's very difficult to check whether you can satisfy some normal distribution assumption to apply t-test. And in that case, it's also very difficult to do permutation because we know it's 6 choose 3, right? The total number of permutation is not big. So you will not have too many null values to calculate. So the null distribution will not be accurate. So in that case, this p-value idea is not so prominent. So that's why we were motivated to just get rid of the p-value, but directly control the FDR by thresholding some summary statistic from data. So if you're interested, you can check that out, and I welcome your questions. So for that, I'm going to just leave it for your own interest, and I'm not going to cover in the class. And I can post a link for my short introduction and a full-length introduction of that work under our lecture video. Okay, so I have said enough for multiple testing. Do we have questions before we move on to our next topic? Okay, so our next topic is the method. I'm going to talk about a bioinformatic method that is very popular for RNA-seq data analysis. It's called DE-seq. And it's not DE-seq2. Just for your information, DE-seq2 is now the state of the art, but DE-seq was earlier. And the interesting thing to think about is that, DE-seq has a very different model from DE-seq2. So the two methods are, I would say, totally different or drastically different. So now let's use DE-seq as an example to explain the model. And given what we have said, I would welcome you to think critically about the issues, possible issues in this model. And let's think why the authors were motivated to change it to DE-seq2. Okay, so that's a question I will leave for you to watch out throughout the introduction. We may not finish it today, but we'll try to cover the key concepts, and then we will continue and finish next time. Okay, So one special thing for the DE analysis about RNA-seq data is that our data are counts. In other words, the t-test, those kind of things are not specifically designed for counts. And usually our number of replicates is not too big, so we cannot really trust the central limit theorem to work to apply the t-test. So that's why we need some count-based model for the DE analysis on RNA-seq data. So the first thing to be aware is that we're working with counts. So for count data, two typical distributions are often introduced, and I'm going to introduce both of them. So the first one is what we call Poisson distributions. Okay, and the first one is what we call Poisson, and the second one is negative binomial, which is something we have seen in the combat paper. That one uses negative binomial, but we didn't talk about that in detail. So now you are going to see the negative binomial in more detail. And before going to that, so let me first introduce one notation to help our discussion. So let's say that we are interested in this xij. I'm going to use this notation. So I will say this is about the count of gene I in sample J. That's the count data we obtain from RNA-seq. And of course, this is after all the pre-processing. That is, you will align your reads to the reference genome. And after the alignment, you will, based on the region for each gene, you will count how many reads are mapped into that gene. So for all these discussions, we are totally ignoring like the alternative splicing, the isoform structure, those kind of things. We're just looking at one gene as a unit. And of course, during the mapping, there are possibilities to consider, like, are you doing unique mapping by throwing out those multiple mapping reads, or are you keeping those reads, right? So we totally ignore those issues here by just assuming you have a count matrix to start with to simplify our discussion. Okay, and when we say distribution, we are considering one distribution per gene, right? Because every gene behaves very differently. And when we do DE analysis, we are doing one test per gene. So each gene I has a test. So in this case, what's considered as repeated samples? The sample J, right? So let's say that we have J go from 1 to N. So in that case, if we have the J go from 1 to N, N is the number of replicates in one condition. In one condition. So these are considered to be IIDs. So we consider XI1 to XIN to be IID from some count distribution. That's the setting we look at here. If we have another set of samples, that we can change this to N1, and we will have XI, or we can call that YI1 to YIN2, just as our two sample t-test notation, and that will follow another count distribution. So I'm just trying to give you some intuition about how the model is related to the data. So the first count distribution we can consider is Poisson. And Poisson is very special that it has only one parameter. So we can say that for gene I, we can probably call this as G. Let's say we drop the I index I for now. Okay, so drop I, so we don't need to carry I everywhere. And the Poisson, we use this notation POI. It has only one parameter lambda, and this lambda is so special. It's equal to both the mean and the variance of a random variable that follows this Poisson. So a very special property about Poisson distribution is that mean equals variance equals lambda. But clearly, this is a very strong requirement, and it may not satisfy, may not fit your data well. For example, let's say you have n data points, you can easily compute their average as an estimator of the mean. You can compute their sample variance as an estimator of the variance. And if you see the two numbers differ a lot, then you are not satisfying the assumption by Poisson. But why is Poisson so popular? The reason is that if you think about the origin of Poisson distribution, it has a very clear connection with what we call the multinomial distribution. And that is very important in RNA-seq. So let's imagine that we consider one sample, okay, just the J sample J, and we consider all genes together. So let me say that gene I go from 1 to n genes to be consistent with our multiple testing case. So if we think from multinomial, this is a multivariate distribution of multiple variables together. If we think about this as x1j, 2xnj. So all the genes that are measured together in one RNA-seq sample, this can be considered as a multinomial process, which means that we are drawing the read counts. Probably I can give them a name. I call the total as capital M. Okay, so I from 1 to n x I j nj. So I can call the sample size, or sorry, I should say library size or sequencing depth of sample J as nj, and I would assign those reads randomly to those n genes based on the proportion of those genes in the mRNA. Okay, so multinomial needs a total, and the proportion vector, I can call that as P1 to Pm. If I assume that the proportions are not sample specific, but just depending on the gene. Because here these samples are considered replicates, so I can assume that they share the same proportion vector. So if we do that, then you can see that if I do the multinomial, you can play with this in R if you're interested. You can see that if I randomly sampling, I can get some numbers for the M genes. And if I repeat them, the count numbers will change slightly, depending on the NJ and PI. And of course, we know that since we have many genes in the human genome, and we know that these proportions, I should say, the summation of PI, I from 1 to m, should be equal to 1, right? All the proportions should sum up to 1. Then we know that each PI cannot be too large. We will not have one gene that dominates all the mRNAs. So if the proportions are small and the sequencing depth is very large, then a very important fact is that we can actually approximate this multinomial by independent Poissons. So we can actually write that for xij, or it's actually, maybe I can say that, I'll write it out for your convenience. I can say that xij is approximately Poisson with parameter lambda as nj times p1. And this one is independent of every other gene. I can write xnj as Poisson with parameter nj pm. So the mean is just the total times the proportion, and they are independent. So this fact happens when nj is going to infinity and all the PIs, P1 and Pm, are going down to 0. So you have a very, very large sample size and you have a very, very small proportion for each gene. Then you can actually approximate this multinomial distribution by Poisson distributions, by independent Poisson distributions. And this is very interesting. And this can simplify our modeling quite a lot. Because if you recall this multinomial, clearly those n random variable counts are not independent for sure, right? You can see, because in the multinomial, if you assign more counts a larger count to one gene, you have to reduce the counts of other genes. So they're dependent in that way. But once your NJ is big enough and your P, the proportions are small enough, that dependence can be ignored. That's why we can use this independent Poisson for approximation. So this is the fundamental reason why Poisson is used so predominantly in the RNA-seq count analysis. But clearly, even though the theory is this, but why do we not observe this Poisson distribution to fit the data well for one gene? Let's say we take one gene, we look at its counts in different samples. So why doesn't Poisson fit that well? The fundamental reason is because I think it's because of the PCR amplification bias, which means that we are not directly sequencing as a multinomial process. Let's say this is the proportion of genes in their mRNA copies, and we randomly draw reads based on the proportion. It's not just as simple as that. We have the PCR amplification, and we also have the mapping. We have those issues all get involved. So that's why the data do not look like perfectly Poisson. But interestingly, in RNA-seq, in single-cell RNA-seq data, when we use the UMIs, the unique molecular identifiers, to remove PCR duplicates, for those UMI-based data, we see that the Poisson distribution actually fitted up pretty well. Okay, so I'll just leave that to our later discussion, but that's enough for Poisson. So what we are going to introduce as our focus here is what we call the negative binomial distribution. And the negative binomial can be considered as a generalization of Poisson by allowing the variance to be greater than the mean. So this one will have two parameters. We can call them mu and phi. So this is the mean, and this is the dispersion for MB. And interestingly, MB can also have another parameterization based on coin tosses. I think that's where some of you first learned it in the probability class. But we're going to defer that interpretation later. So let's first talk about the generalization of Poisson perspective. So one way to think about negative binomial as an over-dispersed Poisson is to think of the additional dispersion introduced by the randomness of lambda. So it can be formulated as a gamma-Poisson mixture. I wouldn't call it mixture. I should say gamma-Poisson hierarchical model. I'm going to change the note for clarity. So in this hierarchical model, we basically consider the Poisson lambda to be a random variable itself. That means, okay, when I draw the sample J, okay, for gene I in sample J, probably I will do this. Lambda J itself comes from another distribution. You may consider this to be the prior in the Bayesian setting, okay? Gamma has two parameter alpha, beta. And then, sorry, I should say gamma J. Yeah, and then my Xij itself would be drawn from the, oh, probably I should say this, my bad. Let's say alpha, lambda Ij. Okay, then my Xij will draw from Poisson. I'll use notation Poisson lambda Ij. Right. So what does this mean? It means that this lambda I for sample J let me see. Let me have some issue here. Okay, yeah, correct. I need to add I to here. So I'm trying to make this clear because I'm saying that I'm considering for each count, Xij, gene I in sample J, its Poisson is not just dependent on versus this. Okay, I'm going to compare these two things, lambda I. So this is the model I used here, I used above, which means that for the gene I just consider the randomness to be in the sample. And every gene has its own Poisson mean, lambda I. But now in this hierarchical model, like I consider the Poisson mean may differ from sample to sample. So I call it lambda ij instead of lambda I. And this lambda ij itself comes from a gamma that's only dependent on gene I. So every gene has its own gamma. So what this means is that this lambda ij introduces some additional variation across sample j. So for sample 1 to sample 2, the j is 1 or 2, they may have different lambda ij. Therefore, the xij are from different Poissons. So doing so, we can actually make the variance of xij bigger than just lambda I. So this additional gamma is going to introduce additional variance to help us fit the data better. And why can this be reasonable? If you think from biology, this is the count. This is the observed count of gene I in sample J. If you believe that there's some biological truth about the copy number of gene I in sample J, then this copy number may still differ a little between across replicates, right? So we know that even though the replicates are considered to be biologically equal, but still there's some fluctuation at biology. So that's why it's reasonable to assume that the lambda ij itself follows some distribution gamma. So that's just the understanding of the gamma-Poisson hierarchical model. So next time we're going to show that putting them together, combining those two things, okay, this is conditional lambda ij, I forgot to put that. So combining them together, I can say that the marginal distribution of xij would be what we call the negative binomial. So we're going to continue from here next time. All right, so we'll stop here. I'll stop recording. And for those of you who are interested in staying for discussion, you can stay in the room and I'll assign you as the host.